Is the Big Bang actually the beginning of the universe, or just where our current equations break down?
That's an excellent question. And what you mean by the Big Bang depends on who you ask that question from. And this is the question that we've been kind of struggling with for decades, if not longer. But it turns out that the meaning of the term Big Bang has been evolving. So the term Big Bang was invented, in fact, by one of the critics of the Big Bang, Fred Hoyle, back in 50s, when he thought you had an alternative where universe was always expanding in the same way, nothing was changing. But the bang was really this idea that universe was much different back then as you go to early times, much denser and much hotter. But then how far back you want to go in time is a question that's indeed goes back to what you were saying. At what point do your equations break down? Keep continuing the same. If you continue using the same equations, at some point, you realize that you reach infinities. Basically, your equations break down. They don't make any sense. They don't make any predictions. And that's what we call Big Bang singularity. But that doesn't tell you what is the Big Bang itself. So the way I like to think about the Big Bang, or the modern interpretation of the Big Bang, is kind of what we mean by a star, which is kind of what we see is that universe emerged from a hot dense state. And we call that the Big Bang. But exactly what was going on inside, or what is going on inside that hot dense state, we don't know. The same way that, 100 or 200 years ago, we didn't know what was going on inside a star. We only see these things in the sky, we call them stars. And we see this thing in the sky, well, you have to look much farther back to actually see things, but we see basically this glow that comes from the early universe. And we call that Big Bang, which is kind of a residue of a hot, dense state. In fact, we did survey physicists on this question, that what do you mean by Big Bang? We surveyed them in a big conference in Copenhagen a couple of years ago. And in fact, very recently, we surveyed them, members of American Physical Society, more than 1,600 of them, asking them, what do you mean by the Big Bang? Is it like universe started at the singularity, or just time has started at the point, or that Big Bang doesn't say anything about a beginning? And 68% of the respondents, in fact, in both surveys, amazingly, it was the exact same number. 68% of respondents say that Big Bang means that universe started from a hot dense state, but it doesn't say anything about the singularity or a beginning of time.
So that hot dense state is very similar to what happens inside stars. Mm-hmm. So do we know anything based on the recent research about the stars that we can tell about the beginning of the universe or the Big Bang?
Well, to some extent, comparison between Big Bang and a star is an analogy. And it is a good analogy, but at some point it breaks down, because a star is, in terms of what we see, it's kind of similar. We see a surface of a star. We cannot see beyond that very well. We could see some other stuff that come, in fact, in a star. So if you look at the sun, the first thing you see, of course, is a bright ball of fire. But it turns out that there are some neutrinos, these subatomic particles that come out of this core of the sun. And we could use that to probe the nuclear reactions inside the sun. We can also measure sound waves, basically as sun quakes, if you want. And those also tell us about the composition within the sun, what's going on, the structure of the sun. And that's been, these observations have been kind of ways that we have managed to probe and understand what's going on inside the sun or other stars. The same does happen for the Big Bang. We can see, well, not directly, but indirectly probe the neutrinos that could have been generated and were generated at the Big Bang when it was a similarly hot and dense state. We could measure quakes or sound waves that were generated at the Big Bang and existed there. But so there are analogies at that level, but the details are different, because in fact, universe is uniform, is expanding, as stars are just sitting there They've been sitting there for billions of years, most of them. So in that sense, the details are different. And as you go to the cores of the stars, the maximum temperatures that you get are maybe billions of Celsius or Kelvin. The Big Bang, however, gets hotter and hotter as you get closer to go to earlier and earlier times. And because of that, at some point, kind of the rules that we know how to treat the stars and have kind of perfected them, those rules break down, and we kind of then in the wilderness, we're not sure what are the right rules to use in such high densities and high temperatures.
What do we mean when we say that there was a singularity at the very beginning of the universe?
Yeah, I mean, we don't mean anything because, in fact, a singularity is a statement of confusion, is a statement about is a lack of meaning, really. So it's in some sense is a paradox, is an inconsistency, but it is telling you that okay, if you use certain sets of rules, then you come up with results that are nonsense. That's not a physical claim. It's just telling you that your sets of rules that you use are inconsistent or incoherent, and we need better sets of rules. So singularity is just a statement about the point at which these contradictions become apparent. And the contradictions are there all along, really. I mean, there are contradictions in this room, and say in various situations, but those are kind of tiny. In some sense, for most predictions, you don't have to worry too much about them. There are two places in the universe that they become big. One is at the Big Bang, and then another is at the cores of black holes. And those are the places that are, we know we don't understand what's going on, but those are places where these contradictions are the biggest.
So it's more of a reminder of human ignorance that we don't 100% know what happened, and we create a concept and we call it singularity.
Right. That's right. Exactly. I think originally it was really a mathematical proof, so mathematical statement. It was called a singularity, but it just basically meant that there's a point that rules break down. But it also tells you that because the rules are breaking down, then you cannot really trust the mathematics that you're using. So it was originally proven by Stephen Hawking and Roger Penrose, who were kind of well-known mathematicians or mathematical physicists. Of course, Roger Penrose won the Nobel Prize for his work. Stephen Hawking unfortunately passed away before that happened. But they mathematically proved that in theory of general relativity, in Einstein's theory of gravity, these points occur. Basically, there are points at which you get infinities, and then you don't know how to extend things beyond that. But those are that just tells you that that's the point where you cannot trust the mathematics of general relativity, and we need better types of models or mathematical theories that describe those points.
Right. So this is related to trying to come up with a theory that would combine relativity with the quantum mechanics, yeah?
Absolutely, yeah. So the description that Hawking and Penrose used, and many cosmologists like myself use to describe universe on larger scales, is a classical description. It's basically uses theory of general relativity, but it ignores quantum mechanics, which is another pillar of modern physics. And the excuse that we have is that these are very larger scales, and quantum mechanics is usually a theory of a small scale, so you don't have to worry about it. But it turns out that the larger scales become small at early times because things are moving apart. So they are large now, but then if you go back in time, everything gets much, much closer. And at some point, you cannot really trust our classical description. So that is really, so what we call singularity, at least most physicists believe that is a symptom of our ignorance of the quantum mechanics or how quantum mechanics talks to gravity. And the hope is that when you actually combine them in a coherent framework, then you replace singularity with something that's more coherent. And we just right now don't know what's the right language to describe it. But in a future theory of quantum gravity, maybe we will find the right language.
Yeah, maybe I will take time to insert some fun sentence here.
Mhm.
You know, I've heard this sentence a lot. I was wondering if you can comment on it. It says, if you are able to explain quantum theory, that means you don't understand quantum theory, which so it seems to be a terrible motivation for someone trying to understand it. So why? What does it even mean?
Well, this is a good point. And in fact, another question that we explored in our survey. So we did, I think, just for context, I told you we did this survey. So we did actually survey of physicists in this conference, and then later all of American Physical Society on 10 questions in fundamental physics. And it turns out that there was no consensus on any of them, except for the meaning of Big Bang that I mentioned to you, that was 68%. There is a little bit of consensus, like the community is 50-50 on one other question that we may get back to, is called a question of inflation. But on any other question, there is no consensus. Basically, there is no majority response. And this question of quantum mechanics is another one, which is been haunting us basically for over 100 years. So we have a theory of quantum theory to compute things, but there's something very weird about it. In a quantum theory that we have, there's a description of the microscopic world, but then there is a description of an observer, like you and I. But somehow, when observers come in, there are different sets of rules that apply to observers than applies to the microscopic world, even though observers like you and I are made out of atoms and molecules and such. So it's kind of bizarre and completely confusing why we have these different sets of rules, basically observations rules for observers, even though we are made out of same subatomic particles. That's, the rules of quantum mechanics apply to. And this has led to a proliferation of interpretations of quantum mechanics, starting from what was known as a Copenhagen interpretation, which is like the original version, where there are different sets of rules. And then there are other sets of rules that somehow kind of brings in information theory and maybe hidden variables, or other sort of weird things into it, which are kind of strange, but kind of tries to make us more comfortable with this bizarre notion of quantum mechanics. For there are two sets of rules. There's a set of rules for observers and a set of rules for subatomic particles. But that's really where there is confusion, and some speculate that maybe this confusion in understanding quantum mechanics has something to do with our kind of inability to combine quantum mechanics with gravity, because they have been both basically outstanding puzzles for the past century. And again, some speculate that they're related. For example, Roger Penrose, who again is one of the giants of the field and won the Nobel Prize recently for his work on the gravity side, speculates that maybe gravity has something to do with what's known as the wave function collapse, which is somehow what observers do when they interact with quantum systems. So somehow observers could do things to quantum systems that other quantum systems cannot, even though observers themselves are quantum systems. And yeah, so maybe gravity has something to do with it. And that's indeed, these are two sides of two different confusions associated with quantum mechanics, how you interact with gravity, how you interact with observers. Whether these two are related to each other is not clear.
Yeah, there is always this, like the dichotomy of two questions. Let's say what happens and then why it happens. I mean, traditional people associate one with philosophy, one with science, or maybe they are same in some contexts. So in the context of quantum mechanics and cosmology in general, yeah, how does that relationship play out? Are scientists focused more on the functionality of some phenomenon, or are we also trying to understand the why behind it?
Well, it's a complicated question. Or I guess maybe a question is simple, but the answer is complicated, because obviously, scientists do ask the why question, that why something happens. And then we come up with a deeper description, but then of course you could keep asking that, and at some point we kind of stop, just because either the problem becomes too hard, or we just don't have the tools to describe the deeper meaning of things. So we've made lots of progress in understanding, say, quantum mechanics, gravity, various complex phenomena. But at some point in all of them, if you push them hard enough, then we're going to stop. Either problems become too complicated, or we're just missing the rules, like the singularity that I mentioned, or the measurement problem in quantum mechanics, or what observers do, or quantum gravity. So there is this question of kind of a deeper meaning or a deeper understanding. Now, is that the same as why that the philosopher means? I think at a practical level it might be, but then I think it could become a matter of terminology. I think we have answers for why for many questions that a scientist would tell you, but is that as deep as a philosopher would want it to be? Maybe not, but I don't know if much deeper answers are to be gained from just purely philosophical discussions.
Yeah. If we go back to the first topic that we started with, Big Bang, to what degree can we accept the possibility of something existing before the Big Bang?
I think it's very plausible. And I mean, if you look at, like, we have in our book a description of, I think, like 27 models of the Big Bang. And roughly half of them, there is a before the Big Bang, and half of them doesn't have before the Big Bang. And in fact, the ideas of before the Big Bang could be very diverse and strange. So, I mean, one possibility is that if the time goes in a loop, so basically if you just, like the Groundhog Day movie, if you ever watched it, it's just if you go back in time, at some point it was the same thing that happened. You have the same story. And I mean, many famous cosmologists have kind of advocated for this as a possibility. There are philosophical questions associated with it, but given that we don't exactly know what the right sets of rules are, it's not clear whether there's a problem or not. So you could have time loops. You could have a universe that's collapsing, then at kind of some point reaches a minimum, and then it decides to expand. It's called big bounce scenarios. We could have ideas where a big universe and a small universe become kind of mapped to each other. So this was idea that Roger Penrose, again, who mentioned before, he proposed. He imagines that a very big universe may just forget about the scale and then becomes a very small universe, like a Big Bang. So this is also kind of bizarre, but really all ideas that we have for the early times are kind of bizarre. Maybe the most prominent one, the most popular one, is this idea of eternal inflation, where you have a universe which is exponentially expanding at a high, very, very fast rate. And then in some regions, some pockets, this exponential rapid expansion stops, and then you get hot Big Bang in that, basically matter and radiation. But most of the rest of the universe, it keeps inflating in that manner eternally. And so basically this, if you go to very early times, you see this kind of wasteland of empty universe, which has a very high density and very fast expansion, but not much else. Basically, there is quantum fluctuations and nothing else. So there are basically all sorts of all manners of possibilities. And the challenge for us is that out of these possibilities, how can we pinpoint what's plausible and consistent with observations? And that's been a challenge, but it's been a challenge that we've been making progress in. In a sense, we are measuring things like what I mentioned before, like sound waves that coming from the Big Bang. Possibly we could see gravitational waves that come from the Big Bang. We haven't seen them yet definitively, but that may come. So these are ripples in the fabric of space-time. So these will actually shed light on the nature of things that could have existed at or before the Big Bang. And hopefully when we kind of have enough evidence, we could find the simplest description that fits the data, but we are still we still have ways to go to get there.
Right. So there are some theories that speculate that maybe universe pops out based on the other universes, and there are others that speculate about the empty universe before the Big Bang. And we also see some progress recently. But empty universe also implies that there is something for it to be empty. Yeah? But I guess it's very difficult for human brain to even grasp the understanding of nothingness, because the evolution probably made our brain to condition to exist in something. Yeah.
Yeah, no, I think this is evolution and intuition is a problem, but in some sense we have overcome that 100 years ago. We started thinking about general relativity and quantum mechanics. We kind of went beyond what's easily imaginable. So it's certainly conceivable to kind of find new languages to describe very foreign concepts. Often it's a mathematical language, but we have to invent new mathematics. Like Newton invented calculus to describe Newtonian mechanics. And I mean, to describe quantum mechanics and general relativity, we have to kind of use differential geometry and functional analysis. They're basically new mathematics that have been invented, either coincidentally invented around the same time or invented before because of the kind of physics that we were seeing. And we could possibly find new mathematics to describe things. Now, sometimes it may take longer than others. But this idea that what it means for a universe to come out of nothing, it's all kind of, again, the question is, what is a mathematical description? And when we say something, the things that we're thinking about are the kind of things that we're familiar with. So in the old language, Newtonian language, we have pebbles, particles, and things like that interact with each other. In the quantum world, we learn about fields, like there is electromagnetic field, there is gravitational field, or geometry of the space and time. And in fact, for anything that you know in the universe, there's a field, there's an electron field, there is a quark field, and things like that. So that's the more modern language. But in that modern language, there is still a space or a space and time, which is some underlying substrates that we define everything on. But whether that itself, is it a fundamental thing or not, the same way that we're thinking about, so basically the way to think about the universe from nothing is that what we learned, say, for example, from Hawking, is that you could have, or from others who invented quantum theory, is that you could generate random electrons and positrons from vacuum. So there are no particles, and then you could make particles, and then some of them could escape the black hole and some may fall into the black hole. So that's how Hawking radiation happens. But this actually happens anywhere. If I have just two plates, two metal plates, put them next to each other, there are actually fluctuations of electromagnetic field in vacuums. There are basically photons that come in and out of vacuum for a very, very short period of time. But these photons actually, there would be some of these photons outside the plates and some of them inside of a plate. But because of the interaction with the plate, it causes actually the plate to get closer together, and that's known as a Casimir force. So there's an attraction force due to this. So these are the effects of vacuum, are actually well studied and established in quantum mechanics. And it tells you that particles are not really fundamental. You may think there are particles, but it's actually could be an illusion, right? According to some observers, there could be particles, and according to others, there may not be a particle. Or it could be more particles or fewer particles, or a combination of them. In fact, when we talk about the Schrodinger's cat, whether the cat is dead or alive, even the fact that there is a cat, that could be a question. There could be one cat, two cats, three cats, or a superposition of as many cats, or zero cats. And then the question is that what happens when you apply that rule to the universe, right? Is there a universe or no universe? And could be The same way that we think about particles popping out of vacuum, we could think of universe popping out of nothing. Now, what that nothing is, it would be a state of a certain state, but that state wouldn't be a state that we're familiar with, right? If all that we know is living in a space-time with 3 space and 1 time, then that could be just a very temporary state of things, and a more general thing may have no space or time or classical geometry in the sense that we understand them. We understand it. So that's kind of the idea, and it's not a very foreign idea. We kind of have seen this over and over again. It's just that to understand how it works, we have to go there, and then, I mean, in laboratories, we can test these in cases that we understand. But in the case of a universe coming out of nothing, I mean, it's very hard to access those conditions, so we don't really have the right set of rules to describe whether that can happen or how that might happen.
Yeah, it would be interesting to test in the future. Maybe in the lab, we can have an experiment to see if we can create a universe.
That's certainly one of the things that scientists have discussed, that whether we can generate a universe in the lab, and there's been a lot of speculation about it. There are certainly some kinds of universe you could generate in the lab, but is that the kind of universe you'd be very interested in? I'm not sure. Yeah.
Yeah, if we talk about the inflationary models, maybe you can also point out what your views on this and whether you find them convincing, or what would be your counter arguments to the existing models about that.
Good. So the question of this kind of goes back to answering the question you asked before: what happened before the Big Bang? And the part of the Big Bang that is kind of well understood is that you have a hot, dense state of the matter at early times, and then the question is what happened before that. So inflation is kind of the most popular answer to that question, is what came before the Big Bang, or what came before this hot, dense state. And historically, it was originated from these puzzles that, I mean, universe is very big and appear to be very uniform. So most notably, we observe this cosmic microwave background, the afterglow of the Big Bang. But then it is actually almost the same temperature, around 2.7 Kelvin, which is minus 270 Celsius. No matter which direction we look at, it's uniform to 1 part in 100,000. And it was very puzzling because, I mean, if universe started at the Big Bang, there was not enough time for light or any signal to propagate from one side of the universe to the other side of the universe. It turns out if you use the mathematics of relativity, the same mathematics that predict there's a singularity, use that, it says that, okay, there's not been enough time for these different parts of the universe to communicate with each other. So how did they come to the same temperature? That was a big puzzle. And there were kind of other related puzzles. For example, why is the curvature so small, which the universe basically has so little wrinkles? You would think if it has a little bit of curvature, it would actually grow over time, but it was just incredibly flat. So the curvature actually didn't grow very much, if there was any of that, basically. On larger scale, it seems to be very flat. And that's been a puzzle, and inflation kind of addresses that. So the idea was that if at some early time you had the period of exponential expansion, so basically what dominates the energy of the universe in early times is a type of vacuum, where it just kind of expands very rapidly, but it doesn't dilute, which is a weird thing, because most matter, if they expand, they dilute. But if you have vacuum or energy in vacuum, expansion doesn't dilute it because it's just energy of empty space. And if you have this acting at early times, it could actually take a tiny region and then make it very, very big. So it could explain why universe is so homogeneous and so have such a small curvature. So these are known as horizon and flatness problem, basically. Horizon problem is why is universe so uniform? And then flatness is that why is the curvature so small? And inflation can actually explain these. So it's certainly where it came from. And then the next thing that was done, which was one of the big successes of inflation, is also predicted fluctuations, basically quantum fluctuations of vacuum in this early phase. would give you seeds for structures that later form galaxies and clusters of galaxies, all sorts of structure that we see around us. They could have been quantum fluctuations during inflation that were then stretched by many orders of magnitude in size, and then they seeded structures that we see today through gravitational attraction. So that was one of the big successes of inflation. So that's why it's very popular and justifiably so. But the issues then emerged after that were kind of problematic for many scientists because there were other predictions of inflation that were harder to kind of wrap your head around, in some sense the same way that quantum mechanics kind of gives you trouble. It's not necessarily rules it out, but it also seems kind of contradictory at some level. For example, one of the issues is what I mentioned before is eternal inflation. And most people who work on inflation think that inflation is actually eternal. That means that even though at some place it may end, on larger scales, most places it doesn't end. Then any prediction that you make for what comes out of inflation would be probabilistic because depending on how inflation ends or where it ends, you assign a probability to it, but depending on how you assign a probability, because it's an infinite universe, so you could weigh different parts differently. You could decide where human lives form. You could somehow give a weight like that, but that depends on how humans or intelligent life comes to be. So that's kind of an anthropic description. So these are questions, right? Because in most of this universe, the eternal inflation universe is a barren universe. Most of it is just expanding exponentially fast and not much happens in it. There are only tiny islands where life can even happen. But then by that token, the problem is, okay, any prediction that comes out of inflation would depend on how you assign probability, because the most probable thing is nothing in that universe as well. And we wouldn't exist, obviously, that way. So that's known as a measure problem. Another problem is, I mean, we don't have one inflationary model. There could be many kind of dynamics and many different types of fields. Nothing that we observe in the standard model of particle physics, the things that we see around us could have driven inflation. But you could imagine there was some field, some sort of particle in the early times, people call it inflaton, but it's just a name. And the issue with that is that depending on what you assume for inflaton, you can get any prediction you want. So no matter what we ever observe in cosmology, there's one inflation model. In fact, probably infinitely many inflation models that could explain it. So question is, can we ever test inflation? Is it a falsifiable framework? And from my standpoint, that's the biggest problem with inflation, which, I'm not sure how we will make progress. I mean, my best approach is that we should come up with alternatives to inflation. And if we can rule out all the alternatives, then probably you are stuck with inflation. But my hope is that there is an alternative which doesn't suffer from the similar problems and could still be successful in explaining our observations.
Yeah, so it's difficult to even test whether that's happening. Yeah, and is it true? I've read somewhere like before. Like what we can observe. Yes, observable universe, and then expansion of the universe. Is it true that as the time goes on, the shrinkage, like the point that we can observe, also shrinks down, which also limits our scientific understanding of the universe?
Yeah, so that's an issue that kind of we have to deal with in the future, because if dark energy dominates cosmic expansion, so it's kind of late time inflation. It's not the early time inflation I was talking about, but in fact, we have direct observational evidence that cosmic expansion is also speeding up today. So we have kind of a much weaker inflation that's happening now. And if that goes on, at some point, basically all the galaxies we see in the universe, they would just kind of move so far away that we cannot communicate with them. It kind of falling into the black hole, but it's like you're inside the black hole, not outside of a black hole. So it's like a black hole inside out. So So everything fall through the cosmological horizon at some point, and we just be sitting in an empty universe. Sometimes people call that heat death because all of the heat, everything just kind of dissipates and falls into this cosmological horizon. So that is an issue. But I mean, it's not that we have to immediately worry about. We will be very alone in the universe, but it would take maybe few billion years, maybe trillion years for us to
In
have to worry
case,
about.
unless the aliens like visit us or something, yeah, similar.
Yeah, I think it will be future generations. Yeah, I would worry more about nuclear holocaust before that happens.
Hope you're finding this conversation interesting, and if so, please subscribe or follow on YouTube, Spotify, and Apple Podcasts. Please also leave a like on YouTube or a review on Spotify, as this helps the show reach more people. You can also leave comments if you have any personal thoughts on the topics discussed during the episode. Now back to the conversation. So there is this idea, scientific paradigm, like the way of measuring things, testable, falsifiable. But how seriously do you take the idea of black swan event? For example, random star exploding in our neighborhood that we never given attention. Or let's say, I mean, extreme case, aliens visiting us, like these black swan events. I was talking to another scientist. He was saying that these days, scientific community is really disregarding this black swan element of cosmos. So how seriously do you think this is a problem in scientific community?
I mean, I think that there's the question is, I mean, how seriously we take it, and the other question is, okay, what do we do about it? Because clearly, I mean, anything can happen. It's a probability, but I mean, the scientific method is that you kind of build your models and theories based on what you know. And yeah, I mean, what you know can predict improbable things, and for that you could plan, but you cannot really plan for the things that you cannot predict. I mean, I think that a smart scientist or a smart politician, or I guess bureaucrat, if you want, has to plan for things according to how probable they are. And obviously, if you don't plan for very improbable things, then yeah, so you may be in trouble. But then again, you cannot just spend all of your time and resources planning for things that are very improbable, because then you lose time and resources for the more probable issues you have to deal with. So I think it kind of makes sense to have a priority kind of a scale, but then it's impossible to plan for things that you don't know, because then it just becomes I mean, a competition of egos is essentially kind of then it becomes like religion, right? Because like really the driving factor for religions, or many religions, is that okay, so there is an afterlife, and there is some sort of reward structure. You don't know how it is, but yeah, that's just going to happen when you die, and then it's going to be a very different very different treatment. There will be justice, and basically everything will be different at that point. So I think that becomes a way of like selling things to people, and something, selling a product. So historically, if you look at the history of humans, in some sense, that's how humans have been kind of pushed to do things that were even against their interests, because they were seeking a higher reward based on things that, I mean, they don't have any evidence for, but they think is promised to them in the heavens or things like that. So it's a higher calling or something like that. So I would worry more that this could be used as a power structure, basically, to generate a sort of religious hierarchy based on who thinks this black swan, who can predict this black swan event for whatever reason. But if we believe in science, then we really should follow the evidence, and nobody really has kind of proprietary access to when these black swan events happen. We all have access to the same data, and based on that, we have to come up with probabilities. Now, we could disagree on probability of things happening, but I mean, we have to use it based on our best evidence and basically scientific method, as opposed to guesses.
Yes, science doesn't claim to have a monopoly on the truth. unlike the traditional religions. Yeah.
That's right. That's right. I think we have to embrace uncertainty. In fact, this is the key catchphrase I believe in from our book is that follow the science. The next sentence is that embrace uncertainty. Basically, if you cannot embrace uncertainty, then you cannot follow the science.
Yeah, it's I agree, but it also goes against the human nature of chasing the certainty. Yeah, because otherwise it gives you the feeling of uncertainty. Is the okay? What's
Mhm.
going to happen?
Yeah, and I think this is one of the paradoxes of life that I think human nature and science, at some level, they are in contradiction with each other. That is it's. I think that the fact that we managed to survive over millennia or millions of years, uh, that's probably means that we have non-scientific urges. Because I mean, there is no scientific proof that you have to live or you have to live in a certain way. Science just is a statement of facts or causes of an effect. But what you choose to do with that information is your choice, and that choice is really one that through evolutionary process we have made, because the ones who have lived are the ones who have survived. But it's not necessarily the one, these are not necessarily the tendencies that gives you the most rational scientific conclusions. These are just the ones that give you the most chance of survival, at least to this point. Now, whether that gives you the better chance of survival from now onwards, or best way of making progress or making most rational decisions, I don't think those are correlated necessarily with each other.
Do you think advancements in artificial intelligence can help with the discovery of new theories because they will not be bound by our evolutionary limits of chasing certainty? Yes.
No, absolutely. That's a great question, and it's one that I mean many, I think, scientists and philosophers are struggling with, including myself. And I mean, certainly artificial intelligence gives us great tools that were not available. But I mean, we have gotten great tools over the years. We have computers, we have airplanes, and that has certainly helped us with achieving many goals that were much harder to achieve in the past, from in terms of learning and achieving whatever goal that we want. But the question of what goal we want to set for ourselves, that's a different question, because that's in fact our choice. And I don't really know whether, I mean, at some level, I suppose what could happen is if the robots take over the world and then we become their subservience, that could solve the problem, because then we don't have to make any choice. That the robots make the choice for us. So that's, I think that's the only scenario I can imagine. If we are enslaved by the robots or by the AI, then we don't have to worry about the problem of choosing things, because they do make that decision. But as long as we still have a decision making kind of power, then we have to decide why we make a decision. And that's, I think, I don't really see AI helping us with that.
Yeah, because there are so many irrational elements associated with making decisions. Yeah, what do you consider valuable, important? We cannot
Yeah.
maybe reach with the cold rational analysis 100%.
Mm-hmm. Yeah, no, absolutely. I mean, I think AI and all the sciences will help us very much in terms of kind of telling us what actions would lead to what consequences with what probabilities. But what kind of consequences we would find fulfilling in 10 years, in 100 years, in 1,000 years. I mean, we humans make sacrifices all the time, because maybe for our children or for our grandchildren, though we may never see them, but we make sacrifices believing that it's good for them. But I mean, at what point does that stop? Yeah, so these are all kind of hard questions that we found fulfillment in strange ways driven by evolution, but they're not particularly logical, and I don't really know. I mean, AI, maybe it will help us with that, but I kind of feel like any other technology, ultimately we are the ones who are making the decisions.
Yeah, imagine you have to marry two people and then you ask, yeah, which one should I do? Okay. Yeah, okay.
Yeah.
Another, I know you mentioned nuclear holocaust. Okay, if we list down the existential threats that humanity faces, which ones are you worried about the most and which ones are you worried about the least?
Well, to be honest, the thing I'm worried about the most is the AI these days. I mean, I've been.
Well, you just said that we can become subservients of the.
Well, yeah, but then of course the AI may decide to kill us all. So I said the best case scenario was that if they become subservient and they make decisions for us. But then of course, if they decide to kill us all, I suppose that could be also an outcome depending on your philosophy of life, which is okay. But I think this is that's a possibility. Unfortunately, I mean, this is I mean, obviously, what's the big news these days is a war in the Middle East, and it's been said that this is the first war that's being driven by AI, at least to some extent. I mean, certainly I've heard this from Voice of America, and there's been all this kind of political trouble with different AI companies with contracting with it was Anthropic that had a contract with Pentagon and they canceled because they didn't like it, and now there's OpenAI. And but then this is the thing, and I mean, now that there's the algorithms that decide who gets to live and who gets to die, and if they get that power, I don't think they're gonna let it go. It sounds kind of dystopian, but yeah, we are literally giving AI power to choose targets, which is one that humans. I mean, it's not that humans were perfect. People obviously made mistakes, but at least humans were making decisions, right or wrong. But now, if we give that power to basically the life of human to an algorithm, then I don't really see that as stopping. And that's the thing actually I worry about the most than a nuclear holocaust. Of course, I mean, if the AI has the power, eventually it will get access to our nuclear codes as well. Yeah, it's a slippery slope.
Yeah, of all the currently unpopular theories regarding the origins of the universe, which one do you think merits the most additional attention, but they doesn't get the attention?
Right. So I think one. I mean, I've worked on many theories of the Big Bang and early universe, and intimately, as I mentioned, these are tied with theories of quantum gravity because the question of what happened at the Big Bang is intimately related to how quantum mechanics and gravity play together, because the meaning of the answer that you want to give uses some language, and that language is a language that must be appropriate at the fundamental level for your theory of quantum gravity. So we are using some language right now about fields and geometry, but that's the language that we've inherited from 100 years ago from forefathers of quantum mechanics and general relativity, but that may be the wrong language. So the one that I'm kind of partial to maybe the most, although I kind of every day I change it depending on the day of the week. But the one that I'm kind of most partial to are the idea that Lorentz symmetry, which is basically what Einstein called the equivalence principle, is not fundamental. In other words, what we think is the speed of light being the fundamental limit of a speed is not as fundamental as we think it is. It's maybe kind of an illusion for us observers at larger scales or low energies. If you go to the point of the Big Bang, maybe speed can be faster than the speed of light, and that's why this side of the universe and that side of the universe can actually communicate with each other at high temperatures, where the universe was much hotter. So everyone could come to equilibrium. And yeah, so there are kind of ideas based on that that could solve kind of puzzles of quantum gravity and initial conditions of cosmology, and maybe other puzzles in quantum mechanics as well, like what we discussed in terms of measurement problem in quantum mechanics, how observers interact with systems. So that's the one that I'm most partial to. But again, depending on the day of the week, it does vary. And like next week, we have a paper that's being published in Physical Library Letters on a different model of the early universe, which is based on based on what's known as quadratic gravity, which is another proposal for initial conditions of universe and quantum gravity. So, so I think that really we want to study all possibilities and go down all the rabbit holes. And ultimately, the real judge is that we want to come up with concrete predictions for all of these models. And the data, maybe not tomorrow, but maybe 10 years from now or 50 years from now, it will rule out some of these predictions. And the ones that will stand, those would be much more established or stronger proposals for early universe.
Can we say a few words about the nature of time at the beginning of the universe? What does it mean? Did we have time existing at the beginning, or like is it related to movement, physical movement, or what is time basically?
Yeah, no, absolutely. I think the question of time, the nature of time, is one of those fundamental questions. That is time fundamental or emergent? So, what we mean by emergent is, for example, when we think about, say, wetness of water, we know water is made out of molecules. So wetness itself doesn't have any fundamental meaning. But on larger scales, you have a description of fluids. Instead of molecules, you could describe them as fluids with some density and some velocity. And then there's also the idea of surface tension, and the water can stick to some surface and then can make a surface wet. So that's an emergent topic. So wetness of water doesn't have any fundamental place in, say, rules of quantum mechanics, but it's something that we are very familiar with. The question is time similar in that sense? Is it just kind of a function of our experience, or is something that fundamentally exists? And it's actually complicated, because, like, if you look at the rules of quantum mechanics and apply it to general relativity, there is no time in it. Like, everything time just drops out. There is no time evolution, it turns out. What you call time is kind of up to an observer. Different observers could call different things time. So there is a way that you could define time, but there's no way to prove that it's fundamental, especially if you go to very early kind of moments of the universe. And there are some proposals that say there is no time. So the description of our universe is timeless. So it's called holographic cosmology. And this is one that, like, I've worked on with collaborators like Kostas Iskanderis. So he was the one who proposed it. So that's one description, that there's no time. Another possibility is that maybe time becomes like a space. So this is in Hartland and Hawking no boundary proposal, where they propose that there's a point where in fact, the quantum origin of the universe, maybe called universe from nothing, it's a timeless description where there are, like, 4 dimensions of a space and no dimension of time. But what that also means is that, the time as we know it, as kind of a direction of evolution where there is no going back, that may not exist at early time. But also it could be that time is the same way as we understand it today. Maybe if a universe is collapsing and bounces, it's the same linear notion of time. In fact, there is another way that it could work. It's called the Janus universe, where you imagine the origin of time is at the Big Bang, or some point in the Big Bang is the origin of time. And then you could go forward or backward, but in both directions, kind of the time increases. In other words, you may think that kind of there is a point which is the point of minimum entropy. And then in either direction you go, the entropy increases. And then you call that basically the direction of time. But the direction of time, so basically the origin of time is at the Big Bang, or some point at the Big Bang. And then there is no before that. Before that is again after that, because time increases no matter which way you go. So there is various ideas that could happen with time. And the reality is, it's a very open question. So you could imagine, whatever you could imagine, probably someone has proposed it.
So interesting. Yes, something that is so central to our experience may not it makes sense in some point, because you can think about time. Where is it? Like, as a physical object, as a physical something you cannot measure. You just see movement of the sun rising up, sun going down. That's all there is. There is just a movement.
Yeah, it's, I mean, again, we have our experience of time. I mean, we already know that that's kind of very subjective. I mean, in some sense, I mean, that's what Einstein first proved, right? Because he showed that time is relative. Different observers experience time differently. But it also, in some level, that also tells you that maybe it's not a fundamental notion, given that different clocks, depending on how they move, they experience it differently. It just if it just depends on the experience of the observer, maybe yeah, you shouldn't really think of it as fundamental. I mean, it's very reasonable. It turns out that there is some notion of time in all the theories that we know, but then the theories that we know are incomplete. Quantum mechanics and gravity are incomplete. Whether at the fundamental level such a notion exists, it's not clear.
Niayesh, thank you so much. It was great talking to you. Just one final question. I mean, the book is really great, The Battle of Big Bang. I would recommend everyone to check out.
Exactly.
Yeah, that's
a very
fine.
nice cover too. And we have a table of all the models we discussed somewhere in the backs. Yeah, we have a very long table with all the models.
Yeah, I'm gonna be honest with you. I was planning to read all of it before this conversation, but I'm halfway there. To be honest with you, I haven't completed it, but so far it's great, and I'm planning to finish it as well. And just a question: so, what are you working on these days? Are you planning a new book? I know you mentioned about the article, so where should people go out and check out your recent work?
Oh, yeah. So you could, of course, go to my webpage, which is nafshordi.com. But then scientists, most active scientists, keep publishing papers. And then you look for my name on Google Scholar, you would find new articles that I do. I work on basically trying to find answers to these mysteries, from the Big Bang to black holes to gravitational waves, all the places where we could get clues about these fundamental questions. I try to make contributions to them, and wherever I find interesting questions. And is there a next book coming? We have talked about it. There are some discussions, but it's kind of early, so I probably shouldn't spoil anything yet.
All right, so we will wait and find out. Yeah, that fundamental urge of trying to understand. Yeah, like Aristotle said, this is his favorite quote. He says, "Everyone by their nature wants to know." Yeah, it sounds simple, but it's like a very fundamental like understanding. Like everyone by their nature wants to know.
Absolutely,
And that
and I
includes you
think
as well and me as well. Yeah.
yes, we all in that category.
Thank you so much. It was great.
Wonderful. Thank you very much, Masud. It was a lot of fun.
Thank you for listening or watching. If you want to stay updated on future episodes, please follow the show on YouTube, Spotify, or Apple Podcasts. Please also consider leaving a like on YouTube or a review on Spotify, as this helps the show reach a lot of people. You can also leave comments if you have any personal thoughts on the topics discussed during the episode. More conversations and solo episodes are on the way in the following weeks, and following the show is the best way to be notified about them. If you would like to reach out to me directly, you can DM me on Instagram at philosophy.everyday. Thanks again for watching, and I'll see you in the next one.